Hey everyone, in this video I will dig deeper into factor analysis. Factor analysis is a little more complex than regression because it has more values and components in the form of tables. Every table has a different meaning, but not all of them are relevant to an analysis. Factor analysis is a dimension reduction technique. It's applied in cases where there are multiple dimensions or variables present. So it helps us to classify or reduce the number of variables so that we can simplify complex data sets. Factor analysis also examines the relationship between two or more variables and to what extent. For example, in a data set of 3000, the respondents express how they feel about online shopping. The objective of that study was to find out the common themes coming out of their answers. But the dataset was too big and complex with so many variables to consider. So the factor analysis test was the best fit in this case. The test revealed 4 dimensions or themes, which are also called as components. Those are sense, feel, think, and experience. In another case where the dataset had 50 elements, it was important to reduce it as much as possible. The factor analysis test helped to bring down the number to 14. Now, to understand factor analysis further, let's see how to apply it on a dataset in SPSS. This is a dataset of about 300 respondents on which I have applied the PCA version of the factor analysis test. The first table we got is the correlation matrix. It's just a simple correlation table. It just shows how the elements inside the dataset are interconnected. Now, the key to remember is that the correlation coefficient value should be at least 0.5 to be considered as a good correlation. We can observe that the correlation between BB1 and BB2 is 0.752, which is considered as a good score as compared to that between BB1 and F2, which is 0.162. Therefore, there is a higher correlation between BB1 and BB2 than BB1 and F2. The next table that was revealed is the KMO and Bartlett's test, which signifies the efficiency of your data. If the efficiency parameters in this table are not met, it could mean that the factor analysis test was not successfully applied. The qualifying criteria for the KMO and Bartlett's test are: the KMO measure of sampling adequacy should be more than 0.5, and the significance value should be less than 0.05 or 0.10. If either of these criteria is not met, then you need to go back to your dataset, process it a little bit, and then rerun the test. In case of this table, the KMO measure is 0.656, which is close to 1, and the significance value is 0.000, which is considered a very good score. The communalities table shows the factor loadings, or to what extent a statement loads on a factor. This is represented through the extraction value. And there is no ideal extraction value as such, and it's represented in decimals, which translates into percentages. For example, here in this table, the first factor loading is for the statement BB1, which shows extraction value of 0.876. This means that the yet undetected variable x is explained by BB1 to the extent of 87.6%. Although this table is relevant, we do not really talk about it in the analysis. The key to remember is that all the statements with similar factor loadings will be related to the same variable. The total variance explained table is the first among many tables that will reveal the number of components or dimensions in your data. This is the key to classifying the elements into identified components. It has 3 subtables, each with 3 columns. Now look only at the first table, which is the eigenvalues table, because it reveals the components and the values based on which they qualify as a component. For instance, in this table, we can see that the first 4 components have a value of 3.321, 1.660, 1.475, and 1.260, which are meeting our qualifying criteria. Now, since the rest of the elements in this table do not have a value of more than 1, they do not qualify as components. The other 2 tables, which is extraction sum of squared loadings and rotation sum of squared loadings, are not looked at because they just reveal the number of components and nothing else. Now the next part of the factor analysis is this tree plot, which is a graphical representation of the identified factors. Now this graph depends entirely on the eigenvalues part of the previous table, which is the total variance explained table. Now in our example, the total variance explained table showed the values of every one of the 9 components. They are simply plotted in this graph. Therefore, the qualifying criteria is also the same. That is, the value of an element should be at least 1 to be considered as a component. Here, the thing to remember is that the plot always slopes downward because eigenvalues decrease in strength with the increasing number of factors. The next table is the component matrix table, which shows the factor loadings of every statement in the dataset toward the identified component. The factor loading value is always between -1 and 1, and the higher the value, the better. A low value, a negative value, or an absent value means that the statement has no relation to that component. So it cannot be classified as a part of that component. For example, in our case, we had identified 4 components. We can see here in this table that the statement PB1, PB2, R1 and R2 show factor loadings for all the 4 components, but their strength is varying. The values which are less than 0.5 are not considered significant enough to qualify as a loading. This table is also not usually explained in the interpretation because it is just a raw form of the next table, which is the key to deciding the final factors in your dataset. The rotated component matrix is the most important table in our factor analysis results. This matrix classifies the observations or the statements in your dataset into different components. For our initial example of 3000 survey participants, we identified 4 key components, which were experience, thoughts, feel, and sense. They are represented as component 1, 2, 3, and 4 in this matrix. This means that every statement in your questionnaire, which is in this case BB1, BB2, A1 and A2, etc., is grouped into components 1, 2, 3 and 4. However, sometimes you will find that one statement can be grouped into more than 2 components. In that case, we will ignore all the components that have a lesser value than 0.5.